We are going to continue our discussion of branching processes in this lecture. Last time we showed that a branching process becomes extinct with probability 1 if the mean number of offspring is smaller than 1. So in this lecture, we are going to look at the converse condition. If the mean offspring number is bigger than 1, and see what we can say about the extinction probability in that case. So let's start with reminding ourselves of notation. So Zn, where n is indexed by the natural numbers starting at 1, you could equally start at 0. Is going to denote the population size in a branching process. We just say it's a branching process. It refers to a stochastic process with the following properties. If psi ij for I equals 1, 2, 3, and so on, and the same for j. So psi ij is a doubly infinite sequence of random variables. If psi ij are IID random variables taking values in the non-negative integers, and Zn plus 1 is given by the sum j equals 1 to Zn of psi nj. So we should think of Zn as the population in generation n and the population in generation n plus 1. The size of the population is the number of offspring of everybody who was present in generation n. Okay, so every individual who was present in generation n dies at the end of this generation, giving birth to a random number of offspring with this distribution psi. Zn could be 0, in which case Zn plus 1 is defined to be 0. So by convention, an empty sum is 0, is the additive identity, which is 0. If Zn is 0, then we are summing from 1 to 0. There is the index set over which the sum is taken is empty. And then the sum is defined to be 0. Okay, so that's the branching process, and we denote the mean number of offspring by mu. So mu is the expectation of any one of these psi ij. It's the same for all of them. So let's say for psi 1, 1. So we are taking the mean of a non-negative random variable. So the mean always exists, but could be plus infinity. Okay, and we have to specify this. We've almost finished specifying the branching process, but to complete the specification, we also need to specify Z1, the initial condition. And you can specify it as you like. We will usually take Z1 to be 1. Okay, so that's a branching process, and we are interested in the probability that it becomes extinct. Okay, so we also defined the event of extinction last time. So, okay, we defined the event of survival last time, and extinction is the event that Zn equals 0 for some n. And if this happens, it's also 0 for n plus 1, n plus 2, and so on. So from that generation on, the total population is 0. So this is the union n equals 1 to infinity of the events that Zn equals 0. Okay, and so the probability of extinction is therefore the probability of this union and this is a union of increasing events. The event Zn equals 0 is a subset of the event that Zn plus 1 is 0. Okay, if Zn is 0, Zn plus 1 is definitely 0, but this could be non-zero, and they could all have 0 offsprings, and then this could still be 0. Okay, so the event Zn equals 0 for is an increasing sequence of events, increasing in n. And so the probability of the union is the same as the limit of the probabilities, and this is by continuity of probability. And so to calculate the probability of extinction, we need to calculate the limit as n goes to infinity of the probability that Zn is 0. Okay, so we are going to turn our attention to calculating this probability now. So we want to calculate this limit. And the way we are going to do this is to use generating functions. So let's recall the definition of a generating function of a discrete random variable. Meaning a random variable that takes values in the integers. So x is a random variable taking values in the integers, then its generating function is defined as follows. So it's a function g, and I'll subscript it by x to specify which random variable we are looking at the generating function of. And so this function is, you can define this function on the complex plane if you like, but we are going to only define it for real numbers. So if you evaluate this function at u, x takes values in the integers, so potentially between minus infinity and infinity. The definition of the generating function evaluated at u is that it's the expectation of the random variable u to the x. X is a random variable, u is a number, a constant, u to the x is a random variable, and we are taking its expectation. And we know how to compute this expectation. It's the sum over all possible values x can take, which could, in principle, go from minus infinity to infinity. U to the k times the probability that x takes the value k. Right? Because the expectation of any function of x is the sum, the function evaluated at k, the probability x equals k. And here the function is u to the x. This is a general definition. We are going to be, the random variables we work with are the population sizes, so they are non-negative. So the sum will only go from 0 to infinity, but I'm defining the sum in general. Okay, and this is defined for all real numbers u, but there is one ambiguity when u equals 0. So what's the issue? If u equals 0, one term in the sum is so u, when k is 0, you have 0 to the 0 times the probability x equals 0. The issue with this term is 0 to the 0 is undefined. So we have to say what we mean by u to the 0 when u equals 0. And by continuity, if you look for any value of u other than 0, u to the 0 is 1. And so if you let u tend to 0, then this term in the sum will tend to 1. So we are going, and so we'll define this function by continuity. So we will take it to be 1 in defining g to the u. G of u, sorry, we will take it to be 1 in defining g0, gx of 0. Okay, so that's a convention. But with this convention, the function will be continuous at 0, or at least right continuous at 0, right and left. It'll be continuous at 0. And we can define what this is. So what is gx of 0? So for, no, we can only define it for positive x. We'll come to that. which is all we are interested in, but we'll come to that in just a moment. Okay, so this was just recalling the definition of generating functions. Now we'll see why this is useful. We are going to compute the generating function of Zn. So let's define some notation. So denote the generating function of So I should write it as G subscript Z subscript n. I'm going to make the notation slightly easier and just write Gn. Okay, so Gn will denote the generating function of Zn. And let's try to calculate this explicitly. So let's try to calculate Gn plus 1 evaluated at u. So this is the expectation of u to the Zn plus 1. And it's not clear how to calculate this from scratch. But if I gave you Zn, then Zn plus 1 is the sum of IID, Zn different IID random variables, and you know how to calculate generating functions for that. So you know how to calculate this expectation conditional on Zn, but we don't know how to calculate the unconditional expectation, or it's not obvious. So let's do it in 2 steps. So let's write this expectation as the expectation of the conditional expectation of u to the Zn plus 1 given Zn. Okay, for any random variables x and y, I can write the expectation of y as the expectation of the conditional expectation of y given x. And this is the Taylor rule. Okay, and now this conditional expectation of Zn plus 1 given Zn equals k is the expectation of u to the xi n1 plus xi n2 plus xi nk given Zn equals k. Now the random variables xi n1, xi n2, and so on are mutually independent and identically distributed, and they are independent of Zn. Zn depends on xi n minus 1 j for different j, xi n minus 2 j, and so on. It doesn't, and so because the xi's as a family are mutually independent, all these are conditionally independent of Zn. So this conditioning is irrelevant. It doesn't change the expectation. And what we are left with is this expectation here, which let me write this out as expectation of u to the xi n1 times u to the xi n2 times u to the xi nk. So it's the expectation of a product of random variables, but the random variables xi and j are mutually independent. So u to the xi and j, which are functions of them, are also mutually independent. And so the expectation of the product is the product of the expectations. So this is the product j equals 1 to k of expectation of u to the psi nj. Okay, since psi and j are mutually independent. Again, k could be 0, in which case the product going from 1 to 0 should be thought of as an empty product, a product in which there are no terms. And an empty product by convention is taken to be the multiplicative identity, which is 1. So you should interpret this product as 1 if k is 0. Okay, so we have calculated the conditional expectation of u to the zn plus 1 given zn equals k. So let me rewrite that. So the expectation of u to the zn plus 1 conditional on zn was the expectation of u to the psi n1, let's say, is the same for any j. Times, it's multiplying itself, zn times, so raised to the power zn. Okay, let me introduce a bit more notation. So let's call, define g of u to be the generating function of the offspring distribution psi. So define this to be the expectation of u to the psi 1, 1. Okay, so this is the generating function of the offspring distribution. Okay, so what we've shown is that the conditional expectation of u to the zn plus 1 given zn is gu raised to the power zn. Okay, and so what's the unconditional expectation of u to the zn plus 1? By the Tower rule, it's the expectation of the conditional expectation. So it's the expectation of gu to the zn Now we define the expectation of u to the zn, that the notation was for that was gn. If I had a u here, it would be gn evaluated at u. I have here not u, but gu, so it's gn evaluated at gu. Okay. So what we've shown is that gn plus 1 evaluated at u is gn evaluated at gu. Okay, so we've got a recursion. And to solve this recursion, I should also tell you what g1 u is. Okay, so what is g1 u? if we take, as we are going to do, if we take Z1 equals 1, we start with one individual, then G1U is the, by definition, it's the expectation of U to the Z1. Z1 is 1, so it's the expectation of U to the 1, so this is U. So G1U is U. Okay, so let's solve this recursion. So we have G1U is U, and Gn plus 1U is Gn of Gu. Okay, so G2 of U is going to be G1 of Gu, which is just Gu. G3U is going to be G2 of Gu. We know what G2 of something is. It's just G of the same thing. So it's G of U. And similarly, Gn of U is going to be G composed with Gn minus 1 times applied to U. Okay, in the lecture notes, I might have started with generation 0, and I might have got Gn of U is G composed with itself n times. Or maybe I didn't. I don't remember what I did in the notes, but the idea is clear. Depending on whether you start with generation 0 or generation 1, you get these expressions. Okay, so that's our formula for the generating function of U. And why did we calculate all this? Well, for one thing, this gives us a somewhat explicit description of the distribution of Zn. So if you calculate this, you can read off the distribution of Zn from that by looking at the coefficients of U. So Gn of U is the expectation of U to the Zn. And Zn can only take non-negative values. So this is the probability Zn equals 0 times U to the 0, which is 1, plus probability Zn equals 1 times U plus probability Zn equals 2 U squared, and so on. So Gn of U is a power series. If you can take the formula for Gn of U and expand it out as a power series, then the coefficients for the powers of U give you all these probabilities. So you can read off the distribution of Zn from the power series expansion of Gn of U. So it's useful for that reason. Another reason it's useful is that what we were interested in is the probability that Zn equals 0, the probability that the branching processes become extinct by generation n. And you can get that simply by setting U equals 0 here, or if you prefer, taking the limit as U decreases to 0. Okay, so the probability that Zn equals 0, I hope you can read the bottom of the screen. If not, I'm reading it out for you. The probability that Zn equals 0 is just the same as Gn of 0. So we want to compute Gn evaluated at 0, and we have a recursive expression for Gn, and we can use this to compute the extinction probability. That's the idea. Okay, that's our reason. That's our other reason for doing this derivation. So let me write that again. The probability that Zn equals 0 is Gn of 0, and that we saw that Gn is just G, the function G composed with itself n minus 1 times. Applied to 0. Okay, now I'm going to draw a picture which I'll justify later. But for now, take a few things for granted. Sorry about that. I have to. For now. So let's compute this. So yeah, I'm going to draw a picture which I'll justify in a bit. Sorry, I'm going to have to stop recording for a moment.